So a spectrogram is just a sequence of spectra, like we have been talking about. So I've been talking about practical spectrum analysis, and that whole story applies to one column, one vertical slice through this image. So each vertical slice here is just the dB magnitude plot of a spectrum, just like we talked about. There's some window that's been used, there's some zero padding factor that's been used, and that's how you get one spectral slice. But then you advance in time, and you typically advance in a way that the window overlaps. So if you have, let's get this up here. So if what we talked about was a window that looks like this, then the next window might look like that. That would be 50% overlap. And people also use 25% overlap quite often. Actually, that's 75% overlap. 25% step, 75% overlap. So that's what gets done to go from just an isolated spectrum to a spectrogram. You are now going through the time axis with successive windows. So these are meant to plot windows at different shifts. And your signal is this big, long sound file that you're working your way through. So now, this is the spectrogram of a speech sample, and down here is the code that I use to compute it. So we read the file, and Sound SC will scale it and then play it, and you want to give it the sampling rate, which you get from wave read. And then if you want a classic spectrogram look, you have to go from the default color map to a grayscale, where darker means louder. So it's dB that gets darker as it goes up. And now you have to choose a window size, and for voice, a very typical choice of window length is 20 milliseconds. That's long enough to resolve the harmonics of the fundamental pitch period. The fundamental frequency, if let's say your minimum fundamental frequency is 100 hertz for voice, then you'll be able to resolve it pretty well. You'll also be able to see formants moving around. But it wants to be short enough that you don't blend phonemes. So you want to have at most one phoneme present in the window at any given time, most of the time. So that's why 20 milliseconds is a very common choice of window length for speech. And this computes the FFT size as the next power of 2 larger than or equal to 4 times the window length. So what we're saying here is that we want at least a factor of 4 zero padding. And it might be a lot more than that if 4 times the window length is not anywhere near a power of 2. We'll go almost to a factor of 8 zero padding. So then we get a window, and here I'm choosing the Hamming window. So I've talked about Blackman, Hahn, and Hamming now. Hamming window has some interesting properties. Its side lobes are basically minus 40-something dB. Think of it as a telephone quality window. Whereas Blackman was like analog studio quality. Rectangular window is like really bad. And then we do our spectrogram and put a title on it, and then restore the color map to what it was. And that's what generated this figure. And so now let's go look at how that was computed. So here's the actual definition. So in an appendix of the book is that spectrogram function. Of course, MATLAB and Octave both have spectrogram functions. The only reason I wrote it myself is that I wanted to be able to put it in the appendix, and I think at the time Octave didn't have one or something like that. So so here's the active loop here. So what we're doing is creating the spectrogram as a sequence of spectra. And so you can see that capital X of colon comma M refers to the mth column of capital X. So your spectrogram in MATLAB is this big matrix where each column is a spectrum. And as you go along the columns, you're going through time. So another way to say it is that across the horizontal dimension of the matrix, you're going through time, and then vertically, it's frequency. So along each column, it is a frequency axis. So capital M is your column number, and so the mth column is given by the FFT of the windowed signal. And so the windowed signal is our zero padded signal, XZP, dot times the zero padded window. XZP is our frame, X frame, with some zero padding. And notice I'm doing zero phase processing here, so I have half the frame and the half of the frame starting at time 0 to m over 2, and then I have the other half way out here. So this is causal processing. I'm sorry, zero phase processing, where positive time goes in the front of the buffer, the zero padding goes in the middle, and then negative time goes at the far right. So that's your zero phase loading of the FFT buffer. And then you apply the window in the same form, and that gets prepared out of the inner loop. So then the frame is really obvious. The frame is just the signal X at some offset for m samples, where the offset gets incremented by the hop size each time. And the hop size is, determined by whether you want 50% overlap or 25% overlap or whatever, or 75% overlap. So that's very straightforward. So you get a frame, you advance the hop size, load the frame into the FFT buffer, in this case in a zero phase manner, so that the window is a zero phase window. Apply the zero phase window, and then take the FFT. The advantage of the zero phase window is that it does not add phase to the signal. So the phase of the spectrum is not modified by the window. There's no time shift of the data. And then here's the plot. So you have a time axis and a frequency axis, and here it is dB, and then you clip it in the usual way. And then the image scale primitive. This is the image plotting facility in MATLAB and Octave that will give you a dB plot between two limits. It's very important to choose these limits reasonably. You want to map your grayscales well, right? You want your grayscales to between white and black to correspond to something good, like between the maximum of your data and minus 40 dB or something like that, and that'll make it look really good. All right, so now let's go back to the plot and see if we can see what's going on. All right, so as I say, this is a plot of the human voice, and so you can see all sorts of things going on here.
Looks like salmon.
What?
I said it looks like salmon.
Looks like salmon.
Yep.
Even in black and white. Yeah. Well, it does. It looks like the side of the salmon that you scrape off and give to your dog. So this is the fundamental frequency, first harmonic, second harmonic, and over here this fuzzy stuff is an H. And so the fundamental is going up and back down, and this is the word high. And people get good at actually reading this stuff. There are people who can read spectrograms and tell you what they're saying. I can do that sometimes, but one of the really clear things you can see is this formant transition here. So you can see a formant, first formant coming down, second formant going up, third formant's going pretty much straight across. That is quite readable as I. So you're going from ah to E in a nice smooth transition. And then down here we have an I. There's a TH that would be hard to identify. I. Then there's an S, which is pretty easy to identify. You can see some voicing going through the S. It's not a purely unvoiced S. Here's another I. You can see the formants here. Kind of a neutral vowel. I is a very neutral vowel, meaning that your vocal tract is close to just a straight cylindrical tube, in which case the formants are equally spaced. And then we have an E and then a ya. So this is the inverse of I, ya. So ya, I, ya. It's just mirrors of each other. And so this whole utterance says, hi, this is Steve Jobs. And we have this, did we use this in one of the homeworks?
No.
We have, maybe it's next quarter we'll use this in one of the homeworks. I hope Apple doesn't mind. This was in the first voicemail from the Next computer. When you got a Next computer, you would open the mail application, you would have an email from Steve Jobs, and it would include a voicemail. And this was the very beginning of it. Hi, this is Steve Jobs. I want to welcome you to the next world. And I think you're going to love your new computer. And a motivational introduction by Steve Jobs. Very exciting. So that's it. That's spectrum analysis and your first look at a spectrogram and how you really do it. And so you really know how to do it now. And then next time you'll see some more demos and applications of Fourier theorems and beyond. And then we'll do filters.